not a stranger to many of us here. To just to introduce her. Dr. Zhang is a professor of mathematics and statistics interdisciplinary program at the University of Arizona. Her research area are in statistical machine learning, high dimensional analysis, non-parametric smoothing, and she has published extensively. And she's also written a book on data mining and machine learning. Her research has been extensively published. She's also the editor-in-chief of the Start and associate editor of other journals, fellow of the American Statistical Association, fellow of the IMS, among many awards that she has received. It's really my pleasure to have you here today and to talk to us about your work. Welcome virtually to Iowa State, and hopefully we'll have a chance to have you in person here, not too long into the future. So please, I don't know whether we have made you a co-host yet, but I'm about to, Bridget, if you can hear me, if you could make her a co-host so that she can share her, there we go. Thank you very much, Bridget.
Okay, thank you so much, Heritage, for inviting me to give this talk. And actually, I have visited Iowa State multiple times. I counted at least 4 times in this recent 2 or 3 years. Actually, I do have another trip coming in March to visit Department of Statistics again. I hope I really can make that trip personally, so we can meet each other in person. And today, actually, I know this is unusual time, and so we'll try to, do our best with this virtual visit and virtual talk. And my talk will be 2 parts. And Heritage suggests me to briefly talk about my research first. So I will spend the first half an hour to very briefly talk about what I have been doing in recent years on the topic of high dimensional data for non-parametric regression. So my title is, break curse of dimensionality for high dimensional data for non-parametric methods. And we know, there are many existing works on linear models, but I will actually show what we have been doing for non-parametric models, which is more complicated. Then in the second part of my talk, I will just share with you about our tripod project and the program and what we have done in past 3 years. By the way, congratulations, late congratulations for getting a tripod phase 1. And we have done this in past 3 years, and there's a lot of experience I can share with you. And so just please feel free to, I think the second part was more interactive. Just feel free to stop me or type your question in the chat about, anything you want to know. I think that's overall, it's a very positive experience for us. And hopefully we will also can identify some opportunities to work together and to try to establish collaborations. As you know, tripod phase 2 just, I think the result just came out and they select 2 out of 12. So that was a very competitive process. And the last 2 winners, both of them actually involve multiple institutes, like 4 or 5 at least. And so we did not get it, and we got a very positive report actually overall. I think the only maybe one major factor we did not get it is we are a single institution. I think our proposal, the scope is really big, it's very ambitious and very great, but it's really hard to do it for one single institute. Okay, and that is why I think my first suggestion is for your phase 2, you should definitely try to look for partners to work together. Multi-institute, definitely that is something will make your proposal more convincing and more powerful. Okay, so without further ado, I will just share with you my first stack of slides. Let me check, where is it? Okay, I think open. Let me open up this first. Let me just retry, okay. This is really experiment. Okay, let's see, this is, I have a multiple screen opening, so I have to make sure I'm sharing it with the right screen. So let me share again. Okay, now I can see my screen. Can you see my screen now?
Yes.
PDF.
Yes, we can.
Okay, great. A very brief talk about what is let me make it full screen if I can. Okay, again, feel free to talk to stop me if you have any questions. Actually, I'm going to talk about 4 papers, so that's really ambitious. All of them are already published. So if you have any questions, I suggest you just read the papers. Okay, I will give you the reference papers at the end. At the same time, let me make sure my time. Okay, I will try to wrap up this within 30 minutes.
Excuse me, I cannot see the full screen. I mean, I cannot see the entire document. It's only a part of the screen.
Yeah.
Oh,
yeah,
really?
same here. Yeah.
You mean you need to use the full screen mode?
I'm using full screen mode. Okay.
If you are using multiple screens,
So Zoom has 2 options.
Oh, is it still half screen? Okay, why don't I do this? I'm going to stop my sharing, make it for full screen first. Then I'm going to.
Yeah. Sorry, and then share the entire screen, the entire desktop or screen or whatever it's called.
Okay.
Then it will work.
Let's see. Share. Resume share. Full screen. How about now?
Now we're good.
It's still?
It's
This is
good.
good. This is good.
Oh, okay, good.
Yeah.
Okay. Let me also open my chat window in case you have any questions. Okay, so now I assume you can see my entire screen, right? Okay, good. What is the curse of dimensionality? And roughly speaking, it's just like a special phenomenon associated with high dimensional data. So what is high dimensional data? And whenever we go dimension higher than 3, we think that's already high dimensional, but because it's beyond our visualization, using computer or using our eyes. This actually phrase was first suggested by Bellman in 1962. Okay, and so I'm going to focus on high dimensional data analysis. So throughout my talk, P will be the dimensionality, Pn is the sample size. So traditionally, most statistical techniques are designed for low dimensional data, basically dimension 3 or usually smaller than 10 or 20. But given the revolution of technologies and computers, our data dimension is getting higher and higher, right? So the analysis we are doing actually also evolving from a fixed P dimension to the T diverges with N, like N increases, P also increases with N, but still at like a small order of N, until the case we call high dimensional or ultra high dimensional data, where P is bigger than sample size N. Okay, so here in my actually research, and I have counted this kind of high dimensional data in many collaborations, including the genetic collaboration on microarray data analysis. Okay, the number of genes, typically we know in our body we have 22,000 genes. but the microarray data typically only have like a few hundred arrays. And also in the imaging data, in the brain imaging data, we have this like images. And we can actually digitalize these images using small grayscale. Then we actually convert these images to a high dimensional data. And also there are networks and astronomical data. As you know, UA has a very one of the best optical and astronomy departments and programs. We are building the largest telescope called LSST now in Chile. And so that largest telescope will survey the whole sky and take pictures of all the stars in the universe. And within a few nights. So within a few nights, you can get a whole image of the whole sky. The idea is to identify the rare phenomenon, okay, and by using this data. So we have to deal with this like a data set. So today I'm going to focus on supervised learning problems. And as you know, so basically we have a data, we have X, I, Y, I, and the goal is to learn the relationship between X and Y, okay? And because we assume our data are actually random realizations from some distributions, typically we assume the relationship is described using this expectation or conditional expectation relationship. For example, conditional expecting of Y given X is Fx. So we need to figure out what is F, okay, from our data. So in statistical machine learning, we call this supervised learning problems. In regression setup, we assume the error is additive. So Y can be written as our true function plus some additive errors. If you handle classification problems, and then this model will be written through some link function, like I say, conditional probability of Y given X equal to F, okay? In the mainstream analysis, there are two big type of model classes. Parametric models, they basically assume the form of F, okay? And the other non-parametric models, they make less assumptions on what F looks like. So today I'm going to focus on non-parametric models. And so parametric models, basically we assume the target function is unknown up to some fixed number of parameters. So typically, if, for example, if we do linear regression, that's the simplest parametric models. We assume the function form is linear in beta, and we only need to estimate the t parameters, okay? For logistic regression, we assume some link function. You also assume this linear relationship hidden in this link function. Alternatively, we all can make some Gaussian assumption. For classification, we assume we have k classes. Each class is from Gaussian. So that assumption is also parametric assumption. Basically, all we need is to estimate k mean parameter and k covariance matrices. Then we actually can construct our classification rule. Okay. And it turns out in the past 20 years, there are a very rich amount of research and active works on how to push these parametric models from low dimensional setup to high dimensional setup. Okay, in regressions in the past, we the only technique we have is ordinary least squares, maximum likelihood estimation, subset selection. If we live in the high dimensional world, we will now we use a penalized OLS, penalized MLE, path finding algorithm, short screening. So all of them are designed to handle high dimensional data. The challenge with high dimensional data is when the dimension is high and even bigger than sample size, we don't even have enough samples to estimate these parameters. If you have 1,000 parameters, you only have 20 samples, okay? You cannot estimate all these betas by using ordinary least squares. And similarly, in classification setup, logistic regression will not work. You will not get your algorithm will not get convergent. You will not converge. You will not get unique solutions. And similarly for RDA, QDA, you will not have enough samples to estimate all the mean vectors and covariance matrices. So we have to modify those lower dimension methods, and that's why we also have penalized logistic regression, sparse LDA, sparse QDA, and support vector machine. and weighted distance discriminator analysis. All of them are designed for high dimensional data. So what is the key to handle high dimensional data? We know how we handle low dimensional data. So a natural direction is reduce data dimension, okay? So I have 22,000 genes. Maybe only a small number of them are useful. So can I just identify the small set of genes and use those to build my classifier or regression? And hopefully in this process, when I get rid of some extra data, when I get rid of a majority of columns, I don't lose information. So, because I want to make sure my model is robust, interpretable, and with high accuracy prediction. Okay. So in order to achieve this, and most existing methods assume this principle called the sparsity principle. Okay. So about sparsity principle, in other words, for the majority of the parameters you are estimates, they are 0. Okay. They don't make a role in your function, and they don't make a role in the prediction. And only small set, okay, here I'm using a set A, and that is a signal. And we only need to identify the small set of covariates and their coefficient, then we can make a prediction. And this is actually a very crucial principle we need to follow when we handle high dimensional data. It's also reasonable. We know, like for example, for breast cancer, although there are so many genes, 20,000 genes, so far based on the scientific research, we only know 2 or 3 of them are very, very useful to screening the breast cancer risk, like BRCA1, BRCA2. So here the main problem is how do I identify this small subset? And then how do I also estimate those coefficients? Okay. And among all these existing works in literature, in the linear regression setup, and the most popular work now is called the shrinkage estimators. And that is how, you have penalized regression, sparse LDA, and so on. Everything, all those techniques try to minimize this penalized objective function. You have a loss function. Then you also impose penalty on those coefficients to shrink those coefficients. The goal is to shrink the majority coefficient to 0. Then we will achieve a sparsity solution. Let me check. Okay. And so I'm not going to talk about this. There's a lot of literature on the choice of penalties. Okay, these penalties are designed for coefficients. So you can have absolute value, you can have squared, and so on, okay? And yeah, and also there are many advances in theoretical research and computational algorithm for these high dimensional linear models. So there are work on Oracle properties, risk bound for finite samples, selection consistency, sign consistency, and short screening consistency. So basically we want to know if my sample size go to infinity, does my procedure have a guarantee to identify the correct subset, okay? To identify the correct, the important features, and also can my estimator can achieve consistency, basically approach the true parameters when sample size go to infinity. Okay? For P bigger than N, it's actually impossible to get any kind of selection consistency. That's why people also have this compromising goals called a short screening consistency. So maybe my model is not exact the subset, but it can cover or capture the true subset, true subset in signals as my final model. Okay, so we will have some small tolerance of false positive selection or false discovery control, and just because this P is so big, it's impossible to really exclude all the noise out unless the signal is really strong. And for the scalable algorithms, you may have heard of LARS, parse finding, parallel computing. So we also have a lot of powerful algorithms to do analysis. Okay, so now I'm going to move on to nonparametric regression. And the nonparametric regression basically don't assume any form of this F, okay? We can have a nonparametric regression, logistic regression, density estimation. So For traditional non-parametric regression, we make the model assumption inference under this smoothness principle. We assume our function f is smooth, or in some function class, and which contains all the nice smooth. By smooth we mean continuous functions or differentiable functions and so on. Okay, so we don't make any assumption about what the function looks like. So non-parametric models are more flexible and robust, and can capture nonlinear patterns. The price we pay for this flexibility usually is computational, and also like a theoretical study is much harder because we make our function space is too big to search the correct, to search the solution, and usually that will actually increase the variance and increase a lot of complexity. Okay, so there are a lot of works on non-parametric regressions, roughness penalty, and locally weighted estimations, splines, kernels, wavelets, and there are also a lot of theoretical properties. Okay, as I mentioned, all of them just build on this smoothness constraint. So I need to penalize our function, its shape, its roughness. So here I give you an example of a cubic smoothing splines. Okay, we want to estimate one function. Here I show you the picture. The scatter plot is our data, and I want to actually estimate a nice smooth function to capture the trend. So this picture actually show you a smoothing splines. So essentially we are minimizing also penalize the regression, but here when the penalization is on the roughness of f. Okay. So the only assumption we make here is f is in second order sublab space. Basically, f is continuous, absolutely continuous, and its second order derivative is integrable. That's all. Okay, and so you'll have to tune the parameter lambda pretty carefully to get the the balance, perfect balance between the fit and the roughness. If lambda is too big or too small, you may have overfitting or underfitting issue. And so that's why actually the middle panel here, can be chosen by using some cross-validation technique or generalized cross-validation technique to choose the perfect trade-off. And that is an illustration for one-dimensional function estimation. For multi-dimensional function estimation, it's much harder. Okay, and typically what we do is we decompose the function into the smoothing spline ANOVA. Basically, we decompose the function into multiple components, which contain main effects component, 2-order interaction, 3-order interaction, and so on. Okay, and then we need to impose some side conditions to assure identifiability of these components. And then we also need to truncate this series somewhere. And if you only maintain the main effects, you will get additive models. And if you truncate up to the second order interaction, you will get interaction models up to second order. Okay. Okay. And so here is the classical, fit if you apply the smoothing spline ANOVA or for the GAMS model. So in this example, we have 4 variables, and you can see we actually have the black curve are the true function, and the red curve is the estimator given by smoothing splines. Okay, it's not too bad. Usually you can see they can get a smooth fit for my curve, for my trend. And what we notice here is for the second row in the bottom row, these true functions, the true functions are 0 function. Actually, they're just horizontal function and at the 0, so it's actually no signal. So in this example, x3, x4, they are actually not important. But if you're just using this smoothness principle, you cannot really get rid of these functions, these components. So at the end of the day, you still have x3, x4 in your final fit, even they are really not important. They actually should be selected out from the process. So how do we do that? Okay, it turns out if you have high dimensional settings, we may expect a lot of 0 functions in my setup. But how actually can use the smoothing splines and to really get those 0 function estimation? That's actually the problem I'm going to solve today. And so the curse of dimensionality is even more severe in non-parametric models because first of all, the function itself are infinite dimensional, okay? without making an assumption about the form, you know, the function space is so huge. In most cases, it just can be spanned by infinite number of bases. So that's actually already high dimensional itself, okay? Just if you want to estimate all the coefficient of those basis functions, is already much bigger than the sample size. Another challenge for the non-parametric regression is the local average. All the non-parametric regression, they are basically trying to borrow information from the neighborhood, okay? And there's a weight, local weight, which controls the contribution of influence of the neighbors. The closer the points to the target, and the higher weight. And it turns out for high dimensional data, you know, this nice like a local structure will be lost, because you push the dimension data from low dimensional to high dimensional to even higher. The data are getting spread more and more because the volume of space is increasing exponentially with the dimension. So you will not really find the close neighbors. All the points are really far away from each other. So that's very hard actually to borrow information from locals. Okay, and so how do we really break the curse of non-parametrics? So we need to borrow the idea from parametrics. So ideally, I still want to reduce dimension of the data. And also I want to construct my function, hopefully it's interpretable and capture all the signals in low dimensional space. Because we don't make any assumption about the function of the form, okay, the form of function, there are many critical questions about the structures of the function we need to ask, okay? So the following questions are really, really crucial when you do the function estimation for high dimensional data. So for example, is F linear, additive, or having higher order interactions? Also, which variables are not important? It does not show in my true function. So here, only x1, x5 are important. The rest are not important. And if x1 is important, I also want to know, is x1 important in a linear form or non-linear form? And if we do a functional PCA analysis, and there is an important problem of how do I select a function principal component, basically eigenfunctions for our PCA analysis. So I'm going to actually, you're going to propose a unified regularization framework which can address all of these questions. Okay, so here I have 4 questions. Essentially, they're just like 4 different papers. When we proposed our first paper, we did not really realize this framework actually is so general, can handle many different questions. Okay. And then it just goes on. So traditional techniques before our unified regularization framework, people have been trying to address these questions in different ways. So for example, there's a work on basis expansion. Okay, I expand my function in terms of basis, I truncate my series, and I apply these parametric approaches. That's one way. Another way is people doing hypothesis testing. Okay, I want to know x1 is important or not. I just set up a null hypothesis and the alternative. I'm trying to construct a test statistic to compute my p-value and so on. As you can see, all these techniques that are really just kind of not a systematic way of detecting the structures. They're kind of a trial and error process. And there's also no theoretical guarantee about that, okay, I can guarantee I can get my structures consistently or correctly and so on. Okay, so the approach I'm going to propose will follow 2 principles. I want to maintain the smoothness principles for my non-parametric regression, but also I want to add a sparsity principle in my function estimation. So basically, we're going to assume a majority of the components are 0 functions, and the remaining signal functions, they are smooth. So hopefully, I can construct some estimator which can automatically, filter out most of the non-important components, and at the same time estimate those important components using my smoothing, framework. And so the operator I'm going to define a new function operator in the space called the reproducing kernel Hilbert space. That's actually will provide a very elegant framework for this operator to work. Okay, so this operator actually has a very important feature. It's called the soft thresholding operators. So essentially, we can shrink functions directly to 0 functions. Remember the picture I showed you, and we will actually get rid of the small noise filter estimations after using this operator. Okay, so here are the slides of reproducing kernel Hilbert space. I'm not going to spend time on this. It's actually a kind of a very specific, topic, and it requires function analysis, function data result. Knowledge. So essentially, reproducing kernel space is just some nice function, and which is a Hilbert space, such a nice, well-defined norm and the scalar and the distance between functions. And the more important thing, it has a kernel. Okay, so this kernel actually is called a reproducing kernel. So in a sense, all my functions can be reproduced. Okay, by this kernel in some way. Okay, and by using reproducing kernel Hilbert space, I can cast my roughness penalty function estimation problem into, I'm solving a penalized objective function, but now my penalty actually is written in the squared norm of RKHS. Okay, so here you can see the second term. Before I have a roughness penalty, but now it has a new interpretation. It actually is a squared of RKHS norms. So these are still traditionals, and traditional setup. If you use this operator, you will get smooth functions, but you will not get sparse functions. Okay, and so we are going to propose a new operator to replace the second operator, and to combine the smoothness and sparsity in this unified setup. Okay. So here is the operator and the JF, and it plays double roles. It can penalize rough functions. It is thresholding small functions to 0. Okay, I'm going to skip this. This is just some like a parametric setup. And it turns out this thresholding function is really powerful. As I mentioned, it actually can handle all the questions I just listed. Right, select the main important and remove, separate the linear and the nonlinear terms, and also select the important eigen functions in the functional data analysis. Okay, I think I plan to have 10 more minutes to finish this. So our very first paper actually was written a while ago. It's called a COSSO. It's called a smoothing and selection operator. And so here you can see this is the operator form, and it's essentially just a sum of the RKHS norm of all the component. Okay. So the nice thing about the COSSO is if you consider a very special nonlinear space, only consider linear space, this COSSO penalty will reduce to less so. Okay, so there is a nice connection between the parametric and non-parametric, by using this operator. It really reduces, less so, and that's why, it actually has a soft thresholding function. Okay, and then we spend time trying to check, okay, whether this operator really can play dual roles. Okay, and first of all, we need to make sure the solution exists, and also we have to solve these problems. And in the traditional smoothing splines, finite presenter theorem is very important. We will change the problem from infinite dimensional optimization to tractable finite dimensional optimization. It turns out the COSSO solution also actually have this nice property. And even you search your function in an infinite dimensional space, but the function, the optimal solution actually can be expanded by the finite reproducing kernel representers. So in other words, you only actually find out n coefficients for these kernels, then you can get the solution. Okay. And then we also study the consistency result of this COSSO. We establish the optimal convergence result to make sure it is smooth function. It can actually capture, it can converge to the true parameter when sample size go to infinity. And but what we care is the sparsity, right? We want to know whether this actually can really get rid of a non-important component or not. And it turns out that yes. Okay, we actually can find an equivalent formulation for COSSO. It turns out that this one has a scalar variable theta j, which is kind of on and off switch. and it will actually automatically select some signals or just discard some signals. So theta j is, whenever theta j is 0, automatically that variable will be, you know, filtered out from the model. So this is really nice, like a property we can actually can have this in or out, you know, switch for our functions. And so there are also selection consistency, and it assures like when in some conditions, the COSSO can guarantee that we will can capture the correct subset. So basically, in the end of the day, if you end up with 5 variables, and that 5 variables is really, you know, when sample size is really big, that's really is a true subset of 5 variables. So in our paper, we have a simulation where we have 60 dimensions, okay? And we try and the important direction, the important dimension is 12, okay? We want to check whether COSSO can really capture these 12 variables in my model and get rid of these 48, the chunks, okay? It turns out the COSSO give a very, you know, impressive performance here. In this table, you can see second row, that's the average sample size given by COSSO. By using, when you use the 5-fold cross-validation, you can see that the average model size is really close to the 12. That's a true signal, okay? And the problem with COSSO is that it's not a Oracle, but that if you are familiar with Lasso, you know Lasso is not Oracle. Here by Oracle, we mean we want to make sure my tuning parameter is when my tuning parameter is chosen properly, okay, I can estimate my function at the fastest rate, okay, and so basically I want to have the achieve some efficiency in my estimation. It turns out the COSSO itself does not possess these nice properties, okay. Basically, if you want to do selection, you have to make sure your lambda go to 0 really quickly. If you want to go to a consistent estimation, the lambda has to go to 0 in a slower way. It turns out those two parameters are actually are not the same. So we have to address this issue. And so then we got this question is, how can we oracleize COSSO? And that is our second paper, and we have this weighted COSSO, we call it adaptive COSSO. We add this tuning parameter, additional adaptive parameter weight, okay, and this weight actually can be chosen adaptively from the data. And by doing this, actually we can show that, and the adaptive COSSO actually has a nice non-parametric Oracle procedure. Basically, you can achieve sparsity, and at the same time, your signal functions can be estimated in the most fastest rate you can achieve, okay? We also build a solution path algorithm for this adaptive COSSO. So overall, adaptive COSSO has better performance than the original COSSO, okay? And so next I'm going to quickly talk about, you know, how can we use this COSSO to solve another important problem, which is called the partially linear regression models, okay? How I can separate my variables. You know, you have a bunch of variables and some of them are important. How do I know which are linear, which are non-linear, okay? And also if it's a linear, can estimate the linear coefficient properly, consistently. And also if it's non-linear, can estimate non-parametric component consistently. So here we just trying to try to extend the COSSO in this framework. It turns out it's not that straightforward. So we come up with a procedure called a LAND. It's a linear nonlinear discovery. So it turns out we have to decompose our function, okay, into very subtle structures. So we have linear space, nonlinear space. Then we have these different presentations into different orthogonal space. Then we come up with another regularization, which actually has 2 penalties. One penalty is for the nonlinear component. The other penalty is for linear components. And these 2 components are orthogonal to each other. And then we have to adaptive, you know, also we make this adaptive by using 2 weights and 2 penalizations and so on, okay. So that's the LAND, and we also actually can show many nice theoretical properties of LAND, okay, solution existence, asymptotics, and also it can guarantee that in the end of the day, and when sample size go to infinity, linear terms will be selected as linear, nonlinear will be nonlinear, and 0 terms will be just thrown out of my model, okay, with the probability tending to 1. So that's actually nice thing about these operators, and you can actually prove very strong and theoretical properties because we have a unified loss function and penalty function. It's much easier to study the properties than rather than those iterative procedure or arithmetic procedures. Okay. So here is one example for the land estimator, and you can see in this case we have actually 3 nonlinear functions, 2 linear functions, and 1 zero functions, and our land procedure can actually nicely separate them and put them in their own categories. Okay, and then we also apply this to Boston housing data. This approach actually can be used for higher dimensional space, but in our paper, we just put in some like a benchmark data set that people use. And we identify some linear coefficient, nonlinear coefficient, and some coefficients which are not important. Let me see the time. Yeah. Okay, so the last thing maybe I should skip given the time constraint is on the functional data analysis, where your data, you don't have multi-covariate data, your data comes in a function form. And the idea is how can, that's functional predictor, how can you use functional predictor to predict my response? And this is a typical example, when you want to predict a protein structure in tissues, and you use this near infrared absorbance spectral trajectories and try to do that prediction. And in the context of functional PCA, people typically trying to decompose, do the eigenvalue decomposition for the covariance process of these curves, and then truncate the process to make predictors, okay? But we have a different view. Actually, in our structure, we found out that truncation is not a good idea. People typically just rank this principal component by their function by their eigenvalues, and keep all the big eigenvalues components and throw away all the components corresponding to small eigenvalues. It turns out that's not really a good idea. And in more and more research, people find out even a PCA, even principal components, they are not leading. They have very small eigenvalues. They can still be very predictive for the outcome. So this suggests instead of truncating, we actually should select the functional principal components, okay, based on their role in the prediction, not really just based on their eigenvalues. So here we also try to extend the idea of our COSSO to this functional principal component, and in this functional additive models. And we also did some like a theory to show that we can have an optimal convergence rate for this estimation. So the ongoing work, okay, you think, okay, so what's now? So now we are trying to do so far what we have talked, so far I've talked about it really just to focus on general additive models, okay, and in reality, okay, and the many covariates, they interact with each other, and so it's also very, very important to identify the interactions between the model, between the different terms. So recently we have done a few papers on this interaction screening for linear models. That is already hard because for p-dimensional data, if you consider 2 interactions, you increase the dimension of data to 2p squared, right? That's actually even more challenging, more bigger than the raw data. So we came up with a few papers on how do I do two-step interaction screening or using partial equation screening. And very recently we did this RAMP, solution path for interaction screening using hierarchical constraint. So this is what we have been doing in the recent 2 years. And right now we are extending the RAMP to the non-parametric setup, okay? And that is even, you can imagine that is like makes it even like a much more complicated complicated problem to work on. Okay, so I think I want to stop here, and take home message is please remember this smoothing and selection operator in RKHS, and trying to obey sparsity principle and smoothness principle, and there are many. This is very exciting area to work on, and there are many broad applications. Whenever you go beyond linear models, okay, you should consider high-dimensional nonlinear models. Okay, I think I will stop here. I want to see whether you have any questions about the research. Before I move, I changed my slides to the second set on tripod. Oh, actually, can you see? Hello?
Well,
If you want to know the references, here is a reference of the paper. Can you see my screen? I'm still sharing my screen now.
no, not right now.
No, not right now. Okay, so if you want to know these papers, okay, here is the references of the papers. I'm sorry I went over too quickly, but yeah, let me see.
I think Chantal has a question for you.
Okay, yeah, sure, go ahead, yeah.
Really nice talk, Dr. Zhang. I have a question about the Oracle property of COSSO. So does it have a selection consistency? Well, if so, will the following procedure obtain the Oracle rate? So first use COSSO to select the predictors, and then use the selected predictors to fit the regression model.
Yeah, that's a very good question. That's really called a two-step estimator. And even in linear models, people have done this. Actually, you can prove it's still Oracle. If you start with a procedure which is already selection consistency, you can use it, okay, to select your models first. After identify the subset, and then you can use your favorite consistent procedures. You don't have to use the same thing. For example, people do this all the time. People find that like lasso actually has a bias, right? Even it can select models well, but the coefficients are estimated really badly because it has a lot of bias. In order to shrink, you shrink too much. And then people do another ordinary least squares followed by lasso. So here, I think theoretically, you can prove it's still selection consistency. Yeah. What makes it hard is to study you make inference. If you want to compute the confidence intervals, and you cannot only based on the second step analysis, because you kind of you have to take into account the variation, stochastic variation in the first step. Because now you are separating your procedure into two steps: selection and estimation. They are not done by a unified framework. Usually, for this kind of a multi-step procedure, it's really hard to do. To compute the, say, variance or construct confidence intervals and so on. So there are some price you pay, but it works. Yeah, it usually works better than just doing one-step procedure in terms of estimation.
I see. Thank you, Dr. Zhang.
Sure. Very good question. Any more questions?
This is not about the paper, but how about discrete variables? If you have a lot of the P is large, but not only some of them are continuous variable, but a significant number of them are discrete.
Yeah, that's good. That's a very good question. We also designed a kernel for discrete variables. Yeah, you can also define a kernel, basically define the distance between, you have dummy variables basically. So the kernel is just an indicator function. So you can actually incorporate those discrete functions, discrete variables in the model. But given that, and when we do our theory, we always assume my function domain is a continuous domain, function is differentiable, and so on. Yeah, for the theory, I'm not quite sure, okay. But for practical implementation, yeah, you can do it, yeah. You can just create some dummy variables and create, I mean, for discrete, you can, if it's a binary discrete, you can just do linear. You don't need to do non-parametric, right? For multi-cat degree, a multi-level, then you can do nonlinear. You create dummy matrices, and then you can define a certain type of kernel on that. Then you can actually, just then the operation and computation is the same as a continuous. Yeah.
So what about multi-category? Not like a
You mean for
ordinal variable, just a categorical variable, yeah.
For the y or for the x?
For the x.
Yeah, multi-cat. Yeah, you can create
And
multi.
you have to produce multiple indicator variables for one.
Yes.
You have to select them in a group or something like that.
Yes. Yeah.
You have a paper for that? I'm really interested in look at that.
Yeah. That's a good question. Yeah, you can select them in group. Yeah. Yes. Right. Yeah, we can talk about it. Yeah, yeah, I think I know some work. Yeah, we can talk about it. Yes, that's a good question.
Yeah. Thanks.
Sure. Okay, so let's just move on, I guess. So I'm going to turn. Can you see my screen now?
It's still the reference.
Oh yeah. Okay, let me make sure. Let me change. It's kind of. Okay, so I need to make my PowerPoint full screen first. Okay, slideshow, and then I go here. I share my screen. Okay. Can you please tell me what you can see now?
Yeah, I can see it.
Yeah, we can see.
Is it a full screen?
Yes.
It's not a full screen. It's not in the presentation mode. It's just
yeah,
but it's fine. It's good.
Let me. How about now?
Now it's good.
Yeah.
It's representation mode. Okay. Okay, so let me talk about UA tripod, and these are for co-PIs, and as you can see, it's representative of 3 communities. By the way, I should say that even we don't get the phase 2, tripod is still continue, and we feel we have a strong community already built on campus. We also got some internal funding at the university level, so we can actually still continue our research activities and other outreach activities. I think I think the purpose of NSF is just to provide you some seed fund to start, okay, and to boost you up. And then eventually, you have to convert your funding mechanism internally at the institute level or some other, resources. So basically, just let you know. So we still have these activities, and I think I can skip this slide. Everyone here know what is a tripod. And for us, we also involve the tripod plus X, okay? And yeah, I think you are at the tripod, HDR tripod phase 1, okay? And we just submit our proposal phase 2. And so there are many tripod related programs because NSF realized it's very important for the 3 communities to work together to work on theoretical foundations of data science. So what are our perspective of what are really foundation of data science? Different groups, different researcher may have different perspectives. So for us, we think we just want to use the principles of mathematics, statistics, theoretical computer science to develop a theory and methods to understand, analyze, and interpret the data. Okay, so we will focus on how does this algorithm work. Okay, we want a very rigorous theoretical framework. We also want to know why does it work, and so when we want to be able to generalize this specific algorithm to more to other situations, to more general settings. We also want to understand the limitations. So we want to know when is this work, when it will not work, and so we can actually do something better. Okay, and it turns out to address all these questions, and one single discipline is not sufficient. So it requires the joint effort of all the 3 communities. Okay. And so can the foundational disciplines, these 3 communities work together? The answer is yes, okay, based on our experience. And so before 2017, and there were very few collaborations among the 3 communities. And here is today. Okay, today you can see we have a lot of activities and outreach, education, research, and So during the past 3 years, our community, we produced 94 papers. That's really a lot. That's a good number actually. Joint publications. We also had opportunity to pursue more funding opportunities, okay, like a center-based or interdisciplinary proposals. So we submitted 33 proposals. Our postdocs, graduate students, gave us 17 posters at different conferences. We also organized 3 conferences in the summer conferences each year at the Biosphere 2, and that was also well attended. That was also uniquely, there's a unique format, so we have actually can attract computer scientists, statistician, mathematician to attend the same conference and to share each other's work. And for postdocs, most of our funding were used to support the postdocs and PhD students. I don't know your case. In our case, our PI or co-PI, and almost does not get any individual funding at all. I think each of PI, co-PI only get a 1 week salary or something in the whole year. I mean, each year. So sometimes people just say, oh, we almost don't get a lot of.
It's the same here.
Yes, yeah. Because again, that funding size, right? Nowadays postdocs, PhDs are very expensive. So. But I think it supported faculty research, because our postdocs, our 4 postdocs, I'm going to talk about them. They are really good. They collaborate with multiple faculties. They have multiple co-advisors. Working with computer scientists, statistician. I personally, co-advising 2 postdocs with other faculties. So that also boosts faculty research. The important thing is that they glue us together. Okay. So you also have 4 co-PIs, right? Anyway, we also have been supporting 14 PhD students. That looks a lot, actually. If you do the money, you do the calculation, I think that's too many. So what we did, actually, we use this like a match funding mechanism, okay? And so students, the faculty with individual fund will have a higher priority to get their student being supported. And also the faculty have to support the 50%, the tripod actually support another 50%. And so that is how we can actually we were able to support 14 students. Otherwise, that's like also hard. I don't know your funding. So for us, it's like a little bit less than $500,000 per year. That's not really much in some sense. Okay, let's just move on. So this is a table to give you an idea of a before tripod, after tripod. Okay, what changes I had made, we have made in the past 3 years. Because before there were no teams and rare interactions. Even there were some interactions that are really just random and just not systematic. And now after tripod, we were able to build 8 teams. Okay, I'm going to talk about their teams, and then write plot papers. And most teams, they have weekly meetings. And also the most important thing we have done is we have a weekly tripod seminar, as you have here. Like it's weekly. In the past 3 years, we have like each year we have like 30 seminar talks. That's really important. And so we were really able to get people together. Otherwise, people are really busy, don't see each other a lot. So on Monday noon, we provide the pizza for free pizza, and then we can attract people to come here to have lunch together. By the way, the pizza money is not from NSF. Okay, NSF forbid us to buy pizza using the grant. So we kind of persuade different departments to chip in the money. That's how the computer science department and also data science institute, they each of them, I think they share the pizza money for us and the coffee and so on. So actually, I think a very good thing about the tripod is you have a, it's really, really important component for us. It's really important institute, and the university actually would like to support us in any way we need. So that's actually, I think, a good leverage you also can use to get, to get matching support from universities. So for example, our conference, also we also get support from university level. So we don't have to pay out the whole conference, because it's very expensive to rent the housing at the Biosphere too, and rent the facilities. And for workforce development, before tripod, all the students are trained separately by different fields. And now we co-advise all the postdocs, PhD students. I think students really benefit from here. They can work with different perspectives, and you can see the postdocs, actually, particularly also can have a very richer experience for research. And outreach, and again, before tripod, each individual field just have their own conferences, have our own communities. And now we have these tripod communities, and we organize many events like Women in Data Science, Machine Learning Literacy Day, High School Outreach. So all these events are actually co-organized by all three communities by tripod. And the 8 research working groups I mentioned, yeah, we have 8 research working groups. We require each group has to be co-led by at least 2 fields, okay, and either CS or stat, or CS stat or CS stats, CS math or math stats, okay, have to be co-led. And it took us a while to really define the research problems. That's actually first semester, people just trying to know each other, try to identify the problems and find the common languages they can talk, they can communicate. And then I think that's why the postdoc and the PhD students are very important, and because they are essentially the workforce, and they trying to take advice from all the faculty researchers suggestions, and they try to implement them. Yeah, we also have weekly seminars and conferences here. So our 8 research working groups, they have their own focuses. It's basically based on our strengths of our current faculty profile, right? We can just build on what we have. We have it turns out our computer science department have a very strong research program on networks, graphs, and visualization, imaging science, and the natural language process. And another for optimization group, and statistical machine learning and Bayesian group, and temporal spatial analysis. Okay, so each group, they have their own, let me see, yeah, they have their own research leaders, participant, and all the meetings happen, most of them happen weekly, and all the meetings are open door, and we have a master calendar. Let me see, do I have master, I'm sure we do have a master calendar somewhere. Yeah, maybe later I can show you our master calendar. And so basically at each day, you can go to master calendar, you can find out which group is meeting where. And all the meetings are open doors, so you can just go to talk with people. And so here is a key participant of research grouping 1. And they actually, this group produced our very first publication in UA history, which is co-authored by CS Math, the 3 community actually joint paper. It's a study of multi-level Steiner trees. And the paper was published in this SEA symposium on experimental algorithms. So that is the one thing I want to talk about, where is the outlet channel for your publication? Where should we publish? If a tripod, we have a group of researchers, so we work together. We have one paper. Where should we submit it to? Okay, should we submit to statistical journal or computer science conference proceedings? We have a different culture. And for us, mostly the first paper actually went to computer science proceedings because they have a very speed review cycle. They had their culture very different. But then after first paper, if you have more work, follow-up work on statistical or mathematical perspectives, then you can send it to stat journal or math journals. And it turns out for us, many of the papers were published in conference computer proceedings, but very top proceedings. And we also, this is another example of group 4 on natural language in process. Okay, they work on trustworthy AI and use machines to reason the text. Okay, and also how to do human intervention, like human in the loop machine learning, and there is like information theory and so on. And okay, so if you like to know, you can go to our website. You can find more information about other groups. And during our phase 1, actually we were able to actually get additional NSF fund. So we got 2 Tripod Plus X grants. Okay, one is on Innovation Lab on this community building infrastructure. Another is on research. We were able to get an NSF RTG grant, and which for training applied mathematicians, and also REU grant, and which is a supplementary fund to support undergraduates for the research. Actually, I think you are you're done with your year 1 tripod, and it's actually a good stage to just write to NSF, say we want a supplementary fund for undergraduate research. It's a very straightforward process, and we were able to support the 6 undergraduate students and starting year 2. And even now, we still actually for this year we have an extension, so we are still supporting undergraduate students. So Tripod actually give you extra additional opportunities of getting other funds. We try to collaborate with institutes outside UA, other universities. Okay, now here is a list of what we have been working with. With Indiana University, we actually got a Tripod Plus X for collaborative research on the graph algorithms. And with University of Utah, they have a very like kind of a world, first-class institute on scientific computing and imaging. So our, visualization and imaging group, have joint papers and proposals with them. And we also, we spent a lot of time working with another university, in another research institute in Mexico, in CMAT. And this is really just like a mathematical institute in Mexico. But the nice thing about CMAT is they actually have a computer science component, statistical and math component. So they actually already have a community, three community in one institute. So we worked together. We actually also organized a conference together for once. But yeah, the highlights. So here is just like some snapshots about what we have been doing. We have a calendar, so you can see. And you can find out what's going on every day at a daily basis. And the second picture is the BioSphere 2 conference. And we organized a very large public lecture series. As a traditional, it's traditionally in UA, organized by College of Science. But for this past 2 years, a Tripod actually has done a Tripod PS have been involving as a main organizer to find speakers, give talks, and so on. Also work with the local high school and invite the high school students to your campus to talk about AI for astronomy. And we also worked with astronomers to attend a Kaggle challenge on astronomy data set. Okay, how do I classify stars? And that's a really good experience. We actually were able to bring the graduate students from mathematics, statistics, Tripod with astronomy to work together. And we organized 2 conferences for the women in data science. That's also like the first event in Tucson. So this is our lecture series. Okay, this is in 2018 on humans, data, and the machines. So 3 key speakers actually are, are from our Tripod. Yes. Yeah, so this talk is like attended by 2,000 people in the big lecture hall, and also like broadcast through the video. It's something really big within the local region. And we have 4 postdocs. So here are like 2 of them. And so Keaton, you can see they involve multiple okay, research working groups. And Keaton just finished, and he actually found a faculty job at the University Texas at Arlington. And Raimondo is still continuing with us for his third year. And so here is a list of our graduate students. We did we were working hard to try to involve female students, minority students, and to support them. And as you can see, we're also trying to distribute our limited resources among 3 programs. Okay, and for the women in data science, one set of a tripod graduate students for women female students. We organize the Tucson events for women, also high school outreach. We also invited high school girls come to do experiment with us using the KNN analysis to do analysis. Okay. And so here are actually just some something I'd like to share with you about the challenges and some experience I'd like to share. I think it's not easy to break cultural barriers, as I mentioned. How to identify the problems and where should I publish where the group should publish the paper and so on. So there's a lot of conversation going on, but all of them are really positive. And in the end of the day, you can publish joint papers and get a joint funding. So that is really good. So nowadays people just used to it. Okay, they established the collaboration and they found out the collaboration are really fruitful. So this is continue. And also I think it's very important again is institutional support. Okay, we actually one of our co-PI has has a lot of experience at the main level. So actually he has a lot of connection with upper level administrator in the provost level office, provost office, president office, and VIP, VPR, vice president for research. So we have close connection with them. We actually visit their office a lot and let them know what Tripod is doing and get their support, particularly for phase 2. Okay, and you should just take action early to make sure you get enough support at the institutional level. Otherwise, it's if we're only based on just work on our own resources, that's not enough. Yeah, leadership is very important. Our co-PI, our 4 co-PI, we meet weekly. Just every week, we all 4 of us meet together and to make all the decisions all together as a group, and also share experiences and share resources. I think that's very important. So this kind of that makes sure we are on the same page, because when you do phase 2, you want to make sure you have the same vision. You understand each other, you support each other. So that's actually very, very rewarding experience for myself. Okay, so yeah, so this is our kind of Venn diagram for the we call it human processing unit, HPI. Yeah, HPU actually, HPU. We have some CS, stats, math. We also have some faculties who have joint appointment across different institutes, different departments. And besides the 3 communities, we actually we are really good at building collaborations with the domain scientists. As you can see, we have a list of faculty professors in other departments like astronomy, information, like linguistic, system industrial engineering, and electronic, ECE, and management information science. And so those, these researchers, they have their own research programs, but they deal with the data science and they need big data analysis all the time. So they provide us a motivation for our problems, and they also provide us test bed, for our algorithm and theory. So that is our strength. So TOA has really strengths in all these programs I just listed here. And then they have like they are ranked as the top in the nation. So we think, you know, even we build foundations, we should make sure, you know, we also can make a translational impact for our work. So our tripod structure, I think I'm almost done. Tripod structure is a kind of a bottom-up structure. You know, you can see this is like what we have. We have a CS, applied mass, that pure mass is a big tent. Then we have a tripod, you know, leadership. That's where the co-PI and the senior personnel, they basically are the backbone of this program. And then we have FTGs and other collaborators, and under the FTG groups, and then we have faculty, students, and researchers. And so we just, you know, the people are just attracted by their research interest, okay? And we don't have really, yeah, so it's just naturally team forms, and teams of teams form, and we believe the teamwork. And so we try to build an infrastructure to enable the collaboration and team building. Okay, and so this is my last slide, and so we prepared this for our actually tripod phase 2 presentation, because we were preparing for the question, what will success look like? And after 3 years, what do you think your tripod can achieve? Okay, and our biggest dream here is kind of like maybe one day data scientists and the scientists make team to win the joint Nobel and the Turing Prize. So basically, we have to do something really major and make a groundbreaking and translational result, such that the scientists can, you know, get the Nobel Prize for it, and the data scientists and computer scientists can get a Turing Award for them. And so we have this big cake that can celebrate the success. And so here is you know, the 2 pictures, and one is a biosphere 2. And we think this is really, really inspiring. You know, although the experiments failed, but this actually can tell us you should try something really ambitious and adventurous. And even, you know, even fail, you'll learn a lot from it. And the picture here, then this is a picture of a black hole. Actually, this is really a very hot topic nowadays. And this is a picture, first black hole picture captured by scientists, and this is actually done by our UA astronomy department. And yeah, so this is like a very nice image. And so that's actually a scientific breakthrough, and we hope, you know, maybe tripod, you know, can provide these platforms and to you know, to nurture this kind of collaborations. Okay, I think that's all I have. I'm 10 minutes beyond my time. I'm sorry for that. Yeah, okay.
No worries, Helen. Thank you.
Mm-hmm. Okay, sure. Yeah, so that's all. If you have any questions, please just either just speak up or type them in the chat window, or maybe, yeah.
So can you say, Helen, this is Radesh Rajan. Can you say a little bit more about mechanisms that you use to encourage collaboration between departments?
Oh, yeah. You know, what I found, what worked is, you know, before I wrote tripod phase 1 proposal, I invite all people together. Okay, I just say, okay, we're going to write this proposal, and you will, you know, we spend a few, you know, weeks to identify people's research interest and form the group. And then I say, okay, now we are going to write the proposal. You have to, each group, you know, if you want to make a case, you have to get together to write this white paper, and so I can include in the proposal. I think that is where it starts. You know, people think, oh, I have to write this proposal, and now I have to work. We have to sit down together and figure out, you know, what problem we are working on, and also I require each working group have to be co-led. You know, you have to be from multiple departments. So then, if you want to get involved in tripod, you have to do this together. And that's actually, I think, it works well. So, you know, they have to figure out the problems and really are willing to, you know, exchange their thought on the questions and are waiting to co-advise students. It's not easy. Yeah, it's not easy. And another thing I want to say, you know, for phase 2 application, actually, we spend a lot of time to prepare phase 2 applications. But again, all the groups did a really good job. They spend, you know, a month to figure out the problem they are doing and so on. And they send me the white paper, very polished. And the project, and you know, in the middle of the writing the proposals, you actually got a lot of ideas. You almost can, you know, have some good ideas for the papers. And even you don't get, you know, found, if your proposal not founded, you still get some research already started. That's one thing. The second thing I realized is like co-advising students is really, really important. If you want to support the students, graduate students or postdocs, you should encourage, you know, those be co-advised by people from different departments. Because if you know, then that, you know, the students have to make a progress, then the faculty have to meet. The problem is that like meeting, people are busy and people maybe have many choices of doing, you know, doing meeting, and they have to just get together. I think students are really crucial. So that's why even we have a, you know, no matter how much fund we have, we always just make sure student support is a priority. Yeah. I think that is true. I want to say another one. I kind of forgot. Yeah, I'll figure out.
Thank you. I don't want to hog up your time. So if anybody else has any question, either type up or use the microphone.
Yeah, I think for collaboration, like also like joint seminar is important. Joint conferences. The problem is that you have to make sure you know, this collaboration can sustaining, can last long. And otherwise, people have an interest, have a passion at the very beginning, and if nothing come out, and if it will not progress, it may not go where. Then eventually, people just die. The interest just die down. So I think it's also important to get people together, see each other, and we were lucky. We have a building which is really close to all the 3 departments, so we can see. All the 3 departments are within one minute walk distance. So we just we also I don't know about you. We also create like a shared space. We have like a you know, a space given by university. So we can tripod, you know, small unit. So people can go there. They feel like they have a, you know, their own environment to work together. So yeah, I think at the very beginning it's hard, but the thing is, as long as you can start, then it will just gradually, it just go on, yeah, automatically in some sense.
Thank you very much.
Sure.
Ranjan has a question.
Oh, yeah. Sure.
He says, do you have thoughts on how to address challenges with regard to initiating new collaborations during the COVID?
Again, that's really hard. That's also a challenge with us. And, you know, yeah, I felt, you know, this is a really unusual situation. People are stressful and initiating new collaboration. Yeah, you are, yeah. So I think like I think in COVID-19 everything had to be virtual. So then I think it's important to have a virtual seminar, virtual discussion like us, and you can have a breakout, you know, breakout room to have a discussions. And what I find is like useful is usually you need you know, to have a maybe you can arrange like sometimes we arrange like 2 or 3 talks in a same theme. Okay, like so hopefully that is interesting by most people. And then if you know, in our conference, we always like when we have a session, we say, okay, this is the imaging session, but we want 3 talks given by statistician, theoretical computer science, and a mathematician. So they all have their perspectives on same problems. And then people just, so when the participants only know part of the 1/3 of the background, the literature. But we find that that's really, really working, because that really making people, know, what are the other, communities' interests and focus. So that kind of, you can organize some sessions, which not, instead of doing random, talks and just, trying to define a theme somehow, make yours, use your seminar time better. But it's really, really challenging. And I always find that, having students is really, really working. To have a co-advised students, so you have to meet with students, then I still meet with my tripod meetings with students. We have working groups. Yeah, let's hope the COVID-19 will be over soon. But this is really
Thank you.
Yeah, sure.
Thank you very much. Thank you very much, and thank you again for giving your seminar today.
Sure.
I appreciate you staying beyond the allocated time.
Yeah.
Look forward to seeing you again soon. Bye-bye now. And bye, everybody, and have a good evening.
Yeah, thank you. Let's keep in touch, okay? Yeah.
Yes,
That'd be great, Helen. Thanks.
Yep.
Yeah, you're welcome. Yeah, it's my pleasure to talk with all of you today. Yeah, I'm sorry. I think I went over time.
Oh, that's not a problem. That's not a problem. We enjoyed it greatly. Appreciate your time.
Yeah, sure.
Thank you.
Take
Bye.
care and stay safe, Helen. Bye-bye now.
Okay, yeah, bye. Take care, everybody. I will see you maybe next March, hopefully. Yeah, if I go to